with the details, the last exercise yesterday that I left. Maybe it's better to do it with the details so that you have in your notes. So the exercise was the function, so left to 0 and then unlock. And we almost everywhere define the function. Is a distributional solution of I think this was the last exercise that I gave you at so after this we have done all exercise, right? So nothing remains which is unclear. Okay, so we have to show that is a distributional solution of in for some t, so let t be positive. dx u0 we have to show this for any test function. So let's start with working with this. So that is equal to 0 TA Now the idea is to consider a change of variable. So let me call it capital phi of tz. I think capital phi, let me see, capital phi of tz. Okay. So capital phi of tz is equal by definition to tx, where x is the usual, with the usual notation. I think it was really capital phi, no? So x is capital X. In this case is simply x plus tz. No? This was our, I think it was our notation, if I'm not wrong. No? It was exactly this one, no? In this case it's just this. So,
no, it was z plus TA.
T. Sorry. Z plus T. Now, let us define also phi hat of Tz is equal to phi of Tx under this change of variable, okay? Let us also recall the change of variable formula. So this is just change of variable. So no. Let me compute now phi phi hat. So this is what? So this is equal to phi hat. So in other words, I can write it also this as phi of Tx equal phi hat of T Z plus Ta. Sorry, phi of T x is Z plus Ta. Okay. Now, if we compute phi hat T is just phi by this formula. By this formula, this is just phi T Z plus Ta plus T. So by the change of variable formula that I wrote yesterday, and also observing that the determinant of the Jacobian of phi is equal 1, Okay. I should end up with this integral. Where u0 of z phi hat if I'm not wrong. So this is simple. Exchanging the integrals. Now this is independent of t, so it goes outside. Now we apply the fundamental integral of calculus. And phi hat is 0 at time capital T by the definition of phi of this space. So we get minus phi hat 0 z is multiplied, sorry, by u0, I forgot, u0 which is not far from being this one. We will actually is the same, because phi hat at time 0, phi hat 0 z is equal to phi of z, phi of 0 z. Because at time 0, capital X is the identity. So, this is phi without hat. So this is equal to minus 0 z, phi 0 z, z, which is exactly. So we put this on the other side of the equality and we get this. So this is the last exercise of today, the oral time. And now we start with another kind of PDEs. So we have seen, so up to today, we have seen first order PDEs of the linear, of the form, general form, well, more or less. At least we are able to recognize, say, such kind of linear PDEs, first order. They are called transport equation of first order linear PDEs. Okay, now we change and we go to more complicated PDEs, in particular to the so-called wave equation. There are several physical motivations for studying the wave equation. I don't want to tell you this, but I just write the equation. So now in R1 plus n, we are interested to the following PDE. Where this is the Laplacian of u. So u in C2, say R1 plus n. UTT equal Laplace of u in 1 plus n. And Laplace of u for a C2 function is just the divergence of the gradient of u, or also the trace of the Hessian of u, as you prefer. In any case, is the sum of the pure second derivatives. Okay. Since here there is no repeated indices, that means for one just today, let me. So it's the sum of the pure second derivative with respect to x, with respect to xi. Okay? Have you ever seen this object called Laplacian of u? Okay. Now, so you see now we have two derivatives in time, two derivatives in space. So this is a linear second order PD, and as such we ask for a C2 solution for the moment, because we need to take two derivatives. Okay. Okay, let's try to imagine some, sorry, there is, no, sorry, there is a constant here. I prefer to put a constant, so let C be positive, maybe I put a constant in front in this form, okay, UTT 1 over C squared. In some sense, t is always replaced by ct in some sense. So when I have to differentiate u, du over dt, if instead of dt I write dct, I have c at the denominator. This is the second derivative, so we have c squared. Okay. You could put c equal 1 if you want, but let's keep the constant. I prefer to keep the constant. Now let's try to imagine, before discussing quickly, one could study this, say, without further conditions on any initial time or whatever. One can imagine, for instance, a solution of this form, e to the ct plus x. Let's see if this is a solution. So if I differentiate with respect to t twice, I get c squared e raised to t plus x. This is ut. If I differentiate, so suppose that in the n1 space dimension, okay, simplicity. Suppose now that I differentiate with respect to x, so uxx, sorry, this is utt, uxx is the same without the multiplication. And so you see that when you divide by c squared, we have that is a solution of 1 over c squared utt equal to uxx. Okay? It's immediate. We could also consider, so this, we have found a solution in time space, in one space dimension, without any boundary conditions. We can slightly modify this. For instance, if we do, what happens if I do this? Well, again, it's clear with the same computation that this is still a solution. These are analytic solutions of the problem. Also, again, with ct minus x, etc. Okay, you can also try to find other solutions, say, using sign, find other explicit solution. Solution of the form cosine of ct, and then some other function of x, cosine or sinus of x, etc. But please do this at home. Just to. So it's curious that these solutions have always the same structure. They are a function. It's clearly that the PDE is linear. So if I consider, for instance, this solution, and I consider this solution, also the sum is a solution by linearity. But these are curious because they have a special structure. They are a function, say they are a function f of x plus ct, and the function of x minus ct, right? At least these special functions here are of this sort. So one wonders, and the sum also is still a solution. So this is curious because if you remember, this recalls the solution of first order PDE, u0 of x, and also this recalls sort of solution of first order PDE, right? u0 of x minus ta. Minus or plus, it depends on a. So depends if, depends on A, but no, if in place of A I put minus A, I get something similar to this, no? So maybe this suggests that there could be a relation, at least in one dimension, just in one dimension of space. So in R1 plus 1, in R2, maybe there is a relation between UTT and between this and our theory of linear first order PDEs with constant coefficients. Why not? And maybe this structure has a more general meaning. Maybe solutions. It's interesting also to say that, remember, we had various geometric interpretations of this, no? So there is something which evolves in time in the direction of the characteristic line. But we can also, so we have studied this in the coordinates Tx. We have studied this in the coordinates, I think, Tx and u, no? You remember? We have not studied this in the coordinates xu. So in the coordinate xu, I have u0 at time 0. Say that u0 is whatever. So this is u0 at time 0. Then we can, this object, we can let time go on. And so, suppose that A is positive, for instance. And then what we see at time 1? At time 1, we see something like this. Right? Same shape which travels with constant velocity towards the right, say. So this is called a traveling solution, because if we have this representation of as a film, as a movie, we just have a picture at time 0, then a picture at another positive time, and we see what happens, then another picture at another positive time. This simply means that if we are able to draw the graph, if we are able to draw the graph in this space, this simply means that we are cutting this three-dimensional space with a plane at time t, 2t, 3t, 4t, and we look at the intersection, and this is what we see. Right? This is simply, so it's sort of movie. No? We have also this possible representation. We cut at time t with some plane, and what we see this. Then we cut a later time, and we see this, and so on. No? So we have, if you look at this, we have u0 that travels toward the right with constant speed. Speed a. Here we have another function which travels toward the left with constant speed. And this says that this curious expression seems to be the superposition of two waves moving this way. So we remember this this interpretation of the space ux. Could be useful. Another way of seeing, because looking at surfaces may be very difficult, three-dimensional space. Maybe it's easier to see the slices, time slices of what happens to the graph of the solution, right? Sometimes, maybe better, just to figure out, instead of the whole surface, may be difficult to, in time space, difficult to imagine, it's maybe easier to imagine a function which, as time goes on, the function travels along right or left. Now, this for what concerns the solution without posing any boundary condition. Now, the problem which boundary condition each PDE admits is not so clear, it's not so easy. Typically, remember, first order PDE was, in some sense, naturally, maybe, coupled with the condition at time 0. This was called sigma, and we decide that reasonable boundary condition to couple with our first order PDE was to say, okay, my solution must be given here. This was a choice. The important point was that this must be transverse to the vector field capital A. That was the crucial point. But of course, I mean, there are other possible conditions that one can assign. Why that? Maybe another one. But this was maybe the simplest. Now here there is the point of what kind of conditions one could assign. So typically one assigns U again the same sigma, and another reasonable possibility is to assign, say, the initial position and the initial velocity. So given, if you want to couple the PDE, you declare the smoothness, the smoothness of the solution you look for. Okay, we look for C2. And if you want a sort of Cauchy problem, or I mean problem with some boundary condition, one can think of putting this. So if you want, given sigma, which is again the time 0. Given U0, smooth enough, U0 in C2 sigma. Okay. Maybe V0 could be less smooth. Maybe V0 could be less smooth, say V0 C1. One can ask, what about this problem? So this is a Cauchy problem for the wave equation, okay? So we are interested in saying something about this. Now, okay, let's do some remark. First remark, interesting remark, is the following: is that in one space dimension. First remark is that we can split the operator formally. I'm writing this, so two derivatives in time minus two derivatives in space. Oh, sorry, there is 1 over c squared here. Okay. We can split as follows. Say 1 over c over c minus x. Okay, and now we check this, what does it mean, this equality? Why is this so? What does it mean, this equality? It means that if I put a smooth function, this linear operator, I acted on a smooth function, so UTT minus UXX. And then let's see what happens if I make acting first this operator decomposition with this. So 1 over c dt minus dx applied to u is simply 1 over c ut minus ux. Okay? Simply this. Then I have to apply this operator to this result. Okay, so let's do this. So 1 over c dt plus dx applied to 1 over c ut minus ux. What does it mean? It means that we find 1 over c squared utt minus 1 over c uxt plus 1 over c utx minus uxx, and we are assuming now that u is in C2, okay? So under this assumption, this cancel, and so it is clear that we get this equality, okay? Okay, so now we could argue as follows. We want to solve this equal to 0. So why don't we solve iteratively first this and then the result to that. Okay, so let me give a name. Now a name is new. So definition, define new equal 1 over c ut minus ux. Okay, nu of dx. Okay. So what does it mean? It means that if we define this, then we are trying to solve the following system. So u, let me write it, u is nu, 1 over c ut, given u smooth enough. And then 1 over c ut plus ux equal 0. If we are able to solve this, then we recover the solution. Okay. So this is the idea of trying to, in one space dimension, trying to look at the solution of the PDE as a sort of system, as a sort of solving, a first order linear PDE in U, homogeneous. We find, maybe we are able to find nu, right? Once we find nu, we put it here, and we have a non-homogeneous now, first order PDE for u. But we have done both homogeneous and non-homogeneous. So maybe this will lead us to the solution, right? So this is the idea, one idea. It's simply, we have discussed this very special structure of this operator, and it's a sort of, it's very symmetric. There is plus here, minus here, reminding a lot of first order theory. And let's see if we can go on with this idea, okay? Remember that we are looking for C2, and so nu, fourthly, must be C1, right? Because I'm differentiating. So C1. Okay, so let me start from this. Another thing is, if I define this, what happens at time 0? Okay, what happens at time 0? At time 0, this is equal to 1 over c ut at time 0 minus ux at time 0. But ut was called v0. Ut was called v0, and this was called, so this is, since everything is very smooth, super smooth, I can also write this v0 of x. And then u at time 0 was called u0. Everything is super smooth, so this should be u0 x time x. Okay? So we also have an initial condition. Huh? Everything. Okay, so now let us concentrate on the first step, homogeneous linear transport equation with constant coefficients. So this is question 1. 1 is homogeneous, linear, first order, PDE, constant coefficients. So let me multiply by c, so that it's really similar to what we have done up to now. So we have the following problem to solve: ut plus c mu x equal to 0, mu of 0 equal 1 over c v0 minus v0. Let me check that I'm not making mistake, that okay. So now this we can solve. So let us write the solution. The solution is what? Can you help me? Utx is equal to what? No, so this is mu 0 if you want. Is what? So it is, let me write here just so this gives us u of px equal to 0 x minus 2. Okay? So we have this, and so we have to simply consider v0 of x minus c. Right? These are, and v0 is this one, so this is equal to 1 over c v0 x minus ct minus u0 x of x minus ct. If I make some mistake, please tell me, because otherwise okay, v0 x minus ct. So now we put our solution v0. So now we look at the second equation. So we have 1 over c ut minus ux equal nu, which is however nu 0 of x minus ct. So let me move, so this is the first, is 2. So ut minus cux equals c mu 0 of x minus ct. So this is, now we have to write down also here ut plus aux equal c of tx. You see, this is exactly a non-homogeneous first order transport equation. This forcing term here we call, sorry for the notation, this c of tx has nothing to do with the constant c there. Okay? Sorry, there is a conflict of notation. This is a constant c which has nothing to do with the right hand side, if this is specific. So maybe you should call another c, I don't know. Which is the smoothness of this c. So nu 0 was c1. So this is c1. C1. And this falls perfectly in the theory that we did last week, or yesterday. So now we have a solution of this. No? Let's try to remember. So let me write it here, the solution, and then we try to make the correct. There is always the risk of making. Then it was what? It was the integral from 0 to t. Then it was the solution. It was the solution of the same transport equation starting at time tau, right? So it was some sort of x minus was it correct? Okay. So now we have just to, without making mistakes, possibly, to copy that formula when in place of A we have minus C, and in place of this C of tx we have this special new right hand side. So let's see if it is possible to not to make mistakes here. So it seems, please correct me, so we have to make, to let, in place of A, we have to put minus C. Okay? So u0 of x plus tc. Then, in place of that, so we have to put here C. And then we have function of x and t. Here in place of t we have to put tau. No? And in place of x, so nu 0. So we have to put in minus c tau. And in place of x we have to write x plus t minus tau c. You agree? Because A is transformed into minus c. So this becomes plus. And this is the new x. So let's see what happens, and then I check if in my notes if I have not made. So d0 x plus tc minus 2 tau c. Tau. So please let me check. u0, n0, yes, n0. Yes, it's correct. It's correct. Okay. It is correct. So now we want to change variable. So now t and x as usual are fixed. Correct? Wrong?
It's like minus, x minus, and so we need to put minus there.
Yes, but a is plus c. A is minus c.
Ah.
A is minus c. So yes, I know, it's easy to make mistakes. But it should be correct, I hope. Huh? Because we are solving, you see, here there is plus a, instead here there is minus, there is, yes, there is minus c. So you have to change that. Now, Tx is fixed, so we change variable and we call this y. So let me call this y. So what happens? I have to do the change of variable. So when tau is 0, this is x plus tc. So u0 of x plus tc, and then you get when, so let me repeat, when tau is 0, this is x plus tc. So when tau is equal to capital T, this is x minus tc. And then I have u0 of y. But then I also have dy, d tau is dy equal minus 2 d tau, say, see. Correct? Huh? This is C, eh? Okay. And so we get what? There is a minus here, and this is 1/2, and this is okay. Right. So this becomes equal to u0 of x plus tc plus 1/2 integral x minus tc, x plus tc, and u0 of y dy. Okay. Now we recall who is nu0. So who is nu0 now? So let me substitute the expression of nu0. So what do we get? We get u0 x plus tc. Sorry, this is tc, tc. Then I have 1/2 x minus tc x plus tc 1/c v0 of x (0y), sorry, 0y minus u0y dy. Now, I can, so this is integrating in the y, so I can use the fundamental theorem of calculus, because it is integral of a derivative, but this cannot be modified. So, I write it as follows, so u0 x plus tc, then I keep this 1/2c x plus tc v0 y dy. So, and then I've written this part, then I have to write this. So what is it? It's minus u0 here, minus 1/2, sorry. u0 evaluated here, plus 1/2, u0 evaluated okay? And then there is a beautiful result that now I want to comment a little bit. So we have found that for a C2 solution, of the Cauchy problem, necessarily UTX has the following expression. So we have 1/2 u0 of x plus tc plus u0 of x minus tc plus 1/2 x minus tc x plus tc v0 of y. So this is called the D'Alembert formula. Now D'Alembert, let me see. No, maybe, sorry. Maybe this. D'Alembert formula. It has a beautiful structure. Let's try to understand it geometrically. Okay? So I want to, into one space dimension, I want to solve the wave equation in this, in our space. So I fix t and x. Now we work in the space, as usual, t is the first coordinate, but it is convenient to put vertically. Okay, so we have tx here. So what is the solution at time t space x there at that point? It turns out that, and remember this is sigma, and on sigma we are assigning u0 and the time derivative with respect, the derivative is v0. Okay, the velocity, let me call it velocity. So we can draw the lines x plus tc and x minus tc. So this is the point x minus tc, this is the point x plus tc. So curiously now, as somehow maybe we could imagine from the beginning, now we have sort of two families of characteristics. One is the family with positive c, and the other with minus c. the value of the solution here must be the value of u0 here plus u0 here divided by 2. So, and therefore u0, it is sufficient to know u0 only at these 2 points. But there is another interesting term, which is the mean value of the velocity here. You see? This is exactly the mean value, because then this, you do this minus this. No? And I mean, is this, you have to integrate this, the velocity on this interval. So you need to know the position at these 2 points, but the velocity at all points, because this is an integral, the velocities at all points, right? So it's much more rich than the scalar one-dimensional case. In the scalar one-dimensional case, the solution was just here, was just the value of u0 here. Here is more interesting. We have the value of u0 here, plus the value of u0 here divided by 2, plus a new term, unexpected, depending on the velocity, the mean value. But in any case, the solution utx is not affected by what happens out of this. This is called light cone by physicists. Out of this cone. What happens here or here does not affect u of tx, because u of tx is interested only at the initial value at these 2 points and the initial velocity here. What happens here is irrelevant. You cannot see. Solution cannot see what happens in this light cone, out of these cones. This then has a lot of physical interpretation. There is the forward cone, the backward cone, but mathematically, in one dimension, we can simply say that if we modify u0 here and here, and it remains the same here, then we don't modify the solution here, right? Because what is the value of the solution here? But the value of the solution here is this plus this divided by 2 plus the mean value of the velocity. The value of the solution here, what is this? Again, the same. So, as soon as I'm interested in the value of the solution in this triangle, this does not see any modification of u0 and v0 out of this triangle. Okay? So-called finite speed of propagation. Huh? Okay, I leave you an exercise. So we have proven that the unique C2 solution of our PDE with that kind of boundary condition is necessarily given by this. Huh? Notice that if I give you remark, let Fg from R to R of class C2 then f of x plus ct. If you want, we can divide by 2. Maybe with the division by 2 is more symmetric. It's nicer. This is a solution of no, it's enough to compute, because when we do so imply u of tx equal this is a C2 solution. Then we do this home exercise. conversely, I mean, if u0 and v0 are times 0, necessarily the solution has the D'Alembert expression. C2 solution with the D'Alembert expression. Yes. So this was based on the idea of splitting the operator. So the wave operator in two dimensions was split into the composition of two first-order linear operators. No? Remember the proof. We can do another. We can do another way. We can use another way to solve the PDE. Okay, I want to show you this. So you see, it's nice how we are relating the theory of first order now to second order. It is because we were able to solve a general inhomogeneous first order linear transport equation with coefficient with C depending on t and x. That since we were able to do this, then we were able to succeed. That's why I started with first order. Okay. Of course, now this formula is very special to one dimension, to one space dimension. The D'Alembert formula that I just cancelled now is for one space dimension. Okay. If you look for similar formulas for two space dimensions, three space dimensions, odd, even space dimension, then they become terribly more difficult. In that case, of course, you have really, instead of having a triangle, you have a cone. Generally, you have a cone. Backward cone, forward cone, etc. The exercise. I want to leave you the exercise. Home is not difficult. The function u written above in the D'Alembert formula can be written as utx equal f of x plus ct into where if v is a primitive of 1 over c is 0, f, g, and c2 in C2 are defined f of y equal to u0 of y plus v of y, g of y equal to u0 of y minus v. Okay. Okay. Now, another way to find this, still very interesting way to find the solution is based on a change of variables. So let's do another observation, remark. Change of variables. So the idea is that the correct variables, in some sense, the correct variables to look in one space dimensions. Okay. The correct variables to look are the characteristic lines. So we try to make this as the new coordinate axis and look how the PDE becomes if we look in this new coordinate system. Okay? So define phi from R2 into R2. Okay? So phi of Tx. So it's somehow similar, not really the same as our diffeomorphism phi that we have used several times in one first order, because the diffeomorphism that we have used there was the identity in the first time component. Instead here this is not the identity. Okay. Let me call this psi and eta. Okay, so psi is this and eta is that. So psi is equal to this and eta is equal to this. And now this diffeomorphism can be inverted explicitly. So we get that t and x. This is just a computation. It turns out that t and x is psi minus eta divided by 2c, psi plus eta divided by 2c. Okay? So this is the inverse phi minus 1. Okay?
For x is divided by 2.
2c divided by 2. Yes. Sorry. Thanks. So this is the inverse, okay? Sending each psi eta to this, which we call t, and to this. Okay, now we write the PDE in the new coordinates. So we call u tilde of psi eta equal u of tx. Okay? What does it mean, this? It means that u tilde is more explicitly u of t xi eta x of xi eta, which now is explicit because t is this. So is psi minus eta divided by c psi plus eta. And now we can differentiate ut, utt, and so on. So you can do this computation by yourself. Maybe I can copy the results if you want. So let me copy. So check this computation. So I don't want these are not difficult. So let me copy. So psi and eta are these two essentially new axes. Check at home that utt turns out to be u tilde psi c squared minus 2 u tilde psi eta t c plus u tilde eta c squared, while uxx turns out to be u tilde c plus 2 O now one should do the computations directly because now there is something that I don't see uxx u tilde. Here it is written something that maybe is not correct. So when you multiply by c squared, divide this, so this should go away with this should remain. I'm not sure. So let's check the results. At the end, what turns out is that when you do this, 1 over c squared this minus this, it's not difficult because everything is explicit. We could do this here, but this is not the case. So it turns out to be apparently minus 4 u tilde xi theta. Please check the computations. Check the computations at home. So, in any case, what it turns out to be equivalent is this new coordinate system that the PD reduces to this. Okay? Which is a mixed second order problem. But you see, from this what do we get? So we get, of course, that this must be independent of eta. So there exists a function, let me call it f, say C1, such that this object is independent of eta. So u tilde of psi must be equal to f of psi, independent of eta. No? Now I want to write this as a, now I put this on the left hand side, so u tilde of psi minus f of psi equal to 0, and then I want to see this as a derivative with respect to psi. So it's sufficient to take a primitive, so capital F be a primitive of f, so capital F is C1, C2, sorry, C2. So what happens here? It happens that we have that u tilde minus capital F, so capital F depends only on psi. This is independent. Sorry. This was independent of eta. Okay, so. Okay. So this must depend only on eta, must depend only on eta. So there exists G in C2 such that u tilde minus f G of eta. And therefore we conclude that u tilde of C eta is the sum of a function of C only and a function of sum of two C2 functions, one of C only, the other of eta only. But eta and C are what we want. No? Again, the same structure. The solution is a function of x plus Ct and f. So this is the way. Please go on with the computations here. That still tells us that there is a superposition of two functions, one of the variable x plus Ct again, and the other the variable s minus Ct. Now, let me give you an exercise. Today the exercises are just computations, are not theoretical exercise. So let me see if it's here. in some sense they are more easy, depends on how the interpretations are. And this we will do maybe on Monday. On Monday we have 5th lecture, so now let U from 0 to t times the unit circle in our n. Now, so U is a vector now, it's not scalar. For the first time in this course, just a vector. U n is larger or equal than 2. And U C2 consider the system one over c squared UTT equal 0t times r, so times r. UTT equal uxx This is a very strange system, by the way. So this is a system of, this is linear, but these two vectors must be orthogonal, and this is a relation between the length of one vector and the length of the other vector, UT tangent vectors. Okay, so consider this system. U is smooth. Then exercise. Suppose that A and B are two C2 functions. Set U of t x U of ts maybe 1/2 a plus s plus ct plus b s minus ct. Then U satisfies. Start. Maybe we don't need it. Let's try to put R here. No need to do periodic things. We could do periodic things, but let's try this. Okay. All right. These are called, they have a name. This is linear, but however, this is non-linear system. So this is called conformality relations. If you think about U to be a map, say, from this into R3, now suppose that n is equal to 3 now. So this maps, say, a space of parameters in R2 into R3. So it's a surface. So it says that the two tangent vectors, ut, at any point they must be orthogonal, right? If in this case, so this tangent vector ut must be orthogonal to ux, maybe 0, because here it is not written they are non-zero. And the length of one tangent vector square is related to the other tangent vector square by this relation. Okay, let's see if this exercise is correct. Okay, now once we have said this, this is a short introduction to the wave equation, mostly in one dimension for the moment. I can show you at least a statement that we will not have time today to conclude. We will do this. Maybe you can try to do by yourself, but it's not easy. So we can generalize. There is a surprising representation result, which generalization of the D'Alembert formula. So we have the following theorem. Okay, so let t and x be t a positive time, x a real number. So we have usual stuff, x and t. Maybe we should go on this. Let me call this triangle here, let me call it tx. Okay, that has an equation. Okay, so let u is C2 of maybe it's sufficient to take omega just an open set containing this. Okay. Okay, so let omega be open containing. So suppose that this is a closed triangle. So we put it closed triangle. Open containing tx. Just a C2 function of omega in time space. Okay. Then there is this representation result. There is something integrated, double integral, actually, tx. And the factor in front is c over 2 utt minus uxx dx dt. plus u of 0 plus u of 0 plus 1 over 2c integral dt 0 1 dy. So this is in which sense this is a generalization of, so this is rather surprising for me, at least, because this is a result which is true for any C2 function. We don't require any PDE here, just C2, smoothness, just C2, and the dimension n equal 1. Okay? Under this assumption, at any point, let tx, so at any point tx, necessarily the value of C2 function must be equal to what we knew before, right? But before u was a solution. And if it is not a solution, there is this, which is 0 if u is a solution. Huh? So there is this curious result. And okay, we don't have time today, but the idea, as you can imagine, is to start to integrate a divergence. Huh? So, proof will continue on Monday, but this is a proof that is based just on the divergence theorem, as the proofs that we made, similar in spirit to the proofs that we made concerning distributional solutions of first order PDE last time, linear first order PDE. So the idea is to integrate a divergence. Which divergence? So notice that UTT over c squared minus uxx is a divergence, right? So the idea is the following. I try to integrate, if this is a divergence, if this is a divergence, then maybe this integral here can be integrated on the triangle. And since it is a divergence, this triangle is Lipschitz, everything is smooth enough, we can apply the Gauss-Green theorem and to write this divergence as a flux, normal flux over the boundary. And maybe, if you are lucky, the normal flux over the boundary could give some boundary term here. This is a boundary term, it's just integrated here. Here the normal is just minus 1, 0. But then there is the integration over this side, the integration over this side, which could give us, who knows, maybe this term here and this term here. So let's try to see this as a divergence. Divergence of what? In time space, which is the vector we field of which we do the divergence. I think it's simply 1 over c squared ut and then minus ux. No? If I take the time space divergence, it means time derivative of the first component plus x derivative of the second one, which is simply this. Right? So this means that if we start with this object, we are integrating a divergence. So maybe something happens when we do Gauss-Green. So this alone is equal to this vector field 1 over c squared ut comma ux scalar product the outward unit normal to the triangle outward. So let me call it nu t nu x, the line integral. So now, this is not the proof. I mean, it's simply an observation that this has a divergence form. This operator has a divergence form. Time space, one space dimension. And so now, if you want to continue, we have first of all to compute the normals. Outward unit normals, this and this. And this is easy. And then we have to start to compute the scalar product and then see what happens. Okay, we will see this on Monday. Okay.